Dear students, today's topic is light emitting diode, LED. Light emitting diode. It is a specially designed a PN junction when it is forward biased, which emits visible light. Light emitting diode is a specially made forward biased PN junction which emits visible light. When a junction is forward biased, electrons from N side and holes from P side, they move to the depletion region. You know what is a depletion region is. In the depletion region, electron-hole recombination takes place. During this recombination process, energy is released because recombination means electrons, they move from conduction band to valence band. Moving of electrons from conduction band to valence band, this is the recombination taking place in the depletion region or at the junction of PN region. Suppose the energy gap of the semiconductor, let it be Eg. See here in the diagram, you can see the P-type material, N-type material. This is the depletion region or the junction, PN junction formed. Conduction band, valence band of P region. Conduction band, valence band of N region. In this region, electron-hole recombination takes place means electrons from the conduction band, they move to the valence band. So here, Eg, the energy gap, that's the separation between valence band and the conduction band. During transition of electron from conduction to valence band, the energy difference is emitted in the form of a radiation. Let h nu be the energy of that radiation. Nu is the frequency. So that h nu should be equal to Eg. So Eg is h nu, nu c by lambda. So Eg is hc by lambda, or from this lambda is hc by Eg. Now depending on the Eg of the given semiconductor, energy gap of the semiconductor, the wavelength of the emitted radiation during this transition will have the wavelength lambda. The Eg values are different for different semiconductor materials. For pure germanium and silicon, the values are 1.1 and 0.7 eV. If we take pure semiconductor, say silicon, energy gap 1.1, lambda, the wavelength, it comes out to be in the infrared region. Similarly for germanium also. Because of this, in case of the germanium or silicon, in case of pure semiconductors, we don't observe the emission of light since wavelength lies in the infrared region which is invisible. In case of gallium arsenide phosphide, the energy gap is 1.9 eV. In this case, lambda comes out to be 653 nanometer, which is nothing but the wavelength of the red light. So, if gallium arsenide phosphide is used to prepare this PN junction, in that case, the transition of electron from conduction band to valence band gives rise to the red color. And LED construction is, say, this is the diagram showing the construction. A PN junction is formed. These are the metal contacts for P region and N region. P region is positive, N region is negative. Here to make a very good electrical contact, some metal coatings are used on both on the upper side of P region and lower side of N region. And this is the symbol of LED with arrow showing the emission of light. And LEDs are prepared by keeping the PN junction inside a transparent a dome or made up of a transparent material. A PN junction is kept inside or embedded in a dome of transparent material like clear colored epoxy resin. When the diode is forward biased, recombination of electron hole takes place. This process gives out light. Then, as the forward biasing, see the diode is forward biased, and as we increase the current, the luminescence increases. Luminescence of this PN junction increases. More is the current, more will be the luminescence. Means the light emitted will be more and more brighter. LED has two leads for connection. One is shorter one compared to the other. One is shorter one, which is nothing but the negative, which is the cathode. The other one is the anode. In case of LED emitting red light, the forward voltage drop across that LED varies from 1.6 to 6 volt to 2 volt. In case of green LED, this forward voltage drop, its range is 2.1 volt to 2.4 volts. This is about the construction of the LED. Now, what is the mechanism of this LED? Here in LED, to prepare LED, it is a specially prepared PN junction which is forward biased. So here, electroluminescent materials are used. Electroluminescent materials which emit light when subjected to an electric field. Electroluminescent materials are nothing but the materials which emit light when they are subjected to an electric field. Such materials are used to prepare the PN junction. Here, let us consider the element gallium phosphide. The normal energy gap for gallium phosphide is 2.25 eV. Here, by adding some impurity to the crystal, localized energy levels are created. See here, you can see in the diagram. The normal energy gap is 2.25. By adding some impurity to gallium phosphide, then localized energy levels, see, you can see the two energy levels here are created, so that when transition takes place to those energy levels or from that level to the valence band, in that case, in case of gallium phosphide, the radiations emitted will have the energy 1.0 eV and 2.1 eV. This 1.8 eV, this transition gives out red light. This transition gives the green light. This is how red and green LEDs are prepared. Some other elements, some other electroluminescent materials are also used, such as gallium arsenide phosphate. These are also used to prepare the LEDs. This is the mechanism. In case of gallium phosphide, light emitted is red emitted R, red and green. Gallium arsenide phosphide, red, yellow, orange light are emitted. This emission of light depends on the material used and how it is controlled. And it also depends on the degree of doping. What type of material, semiconductor materials used, and it also depends on the degree of doping. Now, applications of LED. Infrared LEDs are mostly used in burglar alarm systems. Other LEDs emitting light, are used in digital readout displays like 7-segment displays. In solid state video displays they are used. And image sensing circuits used for picture phone. These LEDs are, in most of the cases, they are used as the indicators. Gallium arsenide diodes used as high radiance source in optical communication. This is about LED. Next is solar cells. Solar cells are the devices which are again prepared by the semiconductor materials forming the PN junction. Solar cells are also the PN junctions. Here, a solar cell is a device which converts incident light energy into electrical energy. Solar cells, they convert incident light energy into the electrical energy. And the solar cells, usually called as photo cells also. They convert light energy into electrical energy. Here, the same thing happens, but here, whenever light is incident, suppose incident light is having energy, say h nu, more than the energy gap of the given semiconductor used here. If the incident light having energy more than the energy gap, then what happens is, here, this light, here, transition of electrons from the valence band, they absorb light. The electrons in the depletion region, they absorb light. They absorb light and they move from valence band to conduction band. As they move from valence band to conduction band, electron hole pairs are created in the depletion region. This constitutes photovoltage across the junction. This is how light energy is converted into electrical energy in PN junctions, which are called as solar cells. And the effect is called photovoltaic effect. The widely used semiconductors in solar cells are silicon, germanium, gallium arsenide, indium arsenide, and cadmium arsenide. But silicon is the most efficient one because the energy gap is 1 eV. So in solar cell, light is absorbed near the junction. That's why the junction is made very thin. The incident light should be absorbed near the junction. So to facilitate this, one of the regions is made very thin so that light can penetrate the cell easily. In a well-designed solar cell, about 50 to 20% of incident light is converted into electrical energy. These solar cells are used in space vehicles, solar panels, which produce or which convert solar energy, that's a light energy, into electrical energy, and which is used for the working of that space vehicle. These solar cells, the photocells, which are also used in intensity measurement, in comparison of intensity of the different sources of light. These are also used for charging the batteries. And this is about the solar cells. With this, we have come to the end of this unit, band theory of solids.